Isomerism is one of the easiest topics in organic chemistry. Let's begin. The basic definition of isomerism says that these are the molecules having same molecular formula but different structural formula, which means when they are written, they look same, but when they are drawn, they are different. Isomerism basically has two types. First one is structural isomerism and second one is stereoisomerism. Structural isomerism can be carbon chain length of the carbon chain, or it can be difference in the functional group or the position of functional group and others. While stereoisomerism is a type of isomerism in which the atoms in the molecules have different configuration. Configuration is basically different configuration. Configuration is basically position of atoms in a space. Position in space. In this video, we'll cover only the structural isomerism. Structural isomerism has total 5 types. First one is the chain isomerism. It means the length of the carbon chain. Second one is position isomerism. It means the position of functional group where it is placed. And third one is functional isomerism. Functional isomerism means the fourth one is metamerism, and the fifth one is stoichiomerism. We'll discuss each of the type. The first one is chain isomerism. Chain isomerism are the molecules or the isomers which have different carbon chain length. For example, if we take the example of butane, has this is N-butane. If we draw its isomer, it would be CH3, CH2, a branch of CH2, CH2 and CH3. Now, this is N-butane. N-butane. It is a straight chain which has 4 carbon atoms, and each of the carbon atom has completed its valency. Sorry, this one is not included, it is CH3. In the isomer, but its isomer is called 2-methyl propane. Why so? This is because it has a chain of methyl on the second carbon. While both of these molecules have same number of carbon atoms and same number of hydrogen atoms, which makes their molecular formula same, but due to difference in their branch, they become isomers as there is difference in their structural formula. I hope you get it. Next one is positional isomerism. Positional isomerism are the isomers that have different position of functional group. Different position of functional group. Different position of functional group. Let's take an example. Take a look at examples. For example, we have CH2, CH2, CH3. Oops, not CH3. OH. This is propanol. Its isomer would be CH3, CH, OH, CH2. Sorry, CH3. I made a mistake over here. It should be CH2. Hence, now look at this example. First one is propanol because it has carbon 1, carbon 2 and carbon 3 with OH attached to the third carbon. But its isomer has OH attached to the second carbon, which makes it 2-propanol. This one is a simple propanol and this one is 2-propanol. I hope you understood the positional isomers. It only differs by the position of functional group to which atom the functional group is attached. The third one is functional isomerism. Functional isomerism are the isomers which have different functional groups. Functional groups are totally different, but they still have same molecular formula. Let's take a look at the examples. The very common example of the functional isomers is glucose and fructose. In glucose, in glucose we have aldehyde, CHO, but in fructose we have ketone, C double bond O, R as well as R. Both these examples make them isomers of each other, but if we talk about their molecular formula, they have C6H12O6. Both have same molecular formula, but different functional group. So these are isomers of each other. Another example of isomers that is written in your textbooks is propanol and ether. CH3 CH2O CH2. Both of these have same carbon atoms 1, 2 and 3. Both of these have same number of oxygen 1 and 1. Both of these have same number of hydrogen, that is 3, 2, 5, 6, 7. 3, 2, 5 and 6, 7. So both of them are isomers of each other. This is alcohol and this is an ether. Next we have metamerism. Metamerism are a type of isomerism in which molecules have different due to different length of carbon on both sides of functional group. This is the most important type of isomerism and a little complicated one because it involves different length of carbon atoms. Carbon atoms have different length around the both sides of functional group, but it still managed to have same molecular formula. For example, we need more space. For example, we have an ether that is CH3 CH2O CH2 CH2O CH3. This is methoxypropane. This portion is methoxy. And this portion is propane because this has 3 carbon atoms. If we draw its isomer, it would be like CH3 CH2O bonded to CH2 CH3. It clearly shows this is ethoxy portion and this is ethane. So it ultimately forms ethoxyethane. Now this isomerism does not have different functional group or different position of functional group. It simply tells about the length of carbon atom around the functional group. Here we have carbon 1 and carbon 2. Here we have 3 carbons. Here we have 3 carbons around functional group on the left side, but we have 2 carbons on the left side in this case. So they both make isomers of each other. In the last type, we'll talk about the tautomerism. Tautomerism is a type of isomerism which depends upon the mobile hydrogen or mobile proton. It occurs in only few molecules which have a mobile hydrogen. Let's talk about its examples. Its examples include ketoenol, Let's look at the structure. C double bond O, CH2, R, it could be any variable group. C double bond, it has 2 carbonyl groups. Here, this hydrogen is mobile hydrogen. It can go to the oxygen which has lone pairs. In the case of ketonal isomerism, the hydrogen will move to the oxygen, forming the ketone. This one is the keto part, forming the keto into alcohol. RCOH. Here the carbon forms double bond with this carbon to complete its valency. O and O are actually. Actually, it's O and O are. Here, the carbon forms double bond with this, and enol is formed here. Here, this part is known as enol because it is this is alcohol and this is ketone. Hence, it is a type of tautomerism which is formed due to the mobile hydrogen. This one is a mobile hydrogen, and it formed the ketoenol isomerism.